In this video, what I want to do is explain the concept of covariance matrix for bivariate normal distribution. That's the goal. But I want to start off with a univariate normal, because we're all pretty familiar with that. So here's our normal distribution. There's our random variable. There's the probability density. And to parameterize this normal distribution, we need two parameters, the mean and the variance. So here we have not a univariate normal, but a bivariate normal. So we got two random variables, x and y, and we can imagine some sort of a z-axis on which you'd have the probability density of the joint values of x and y. So up here, there was a single mean. Down here, we have to consider two means, the mean of the x random variable and the mean of the y random variable. And therefore, the mean isn't presented like this. Rather, it's presented as a vector of these two means, this guy here and this guy here. Now, with a univariate, we have a rather simple way to measure variability, and that's with variance. With a bivariate normal, it gets a lot more complicated. This is the covariance matrix, and that's really the subject of this video. So, if we look at the covariance matrix, it's got these components. This is the variance of the x random variable. This is the variance of the y random variable. And in these corners, we have identical entities which reflect the covariance of x and y. So let's think about what we mean by covariance. So here I've got the heights of some individuals, and here we've got some weights. So those are our random variables, and we've got a scatter plot. And we're going to calculate covariance like this. And in words, we can say that it's the expected value of the cross product of the deviations between two random variables and their expected values, which is actually a mouthful and a little bit hard to understand. So let's think about how we're going to calculate that. So what we're going to do is we're going to take value of height, subtract that from its subtract from it its expected value. The value of weight, subtract from it its expected value. Multiply those together, and the expected value of all those things is going to be our covariance. So let's think of this weight relationship with height. If we think about these guys here, what I've drawn are these guidelines. There's the expected value of height. There is the expected value of weight. So if we think about these guys here, the difference between height, the observed values of height, and their expected values of height is going to be positive. So, see that? And in terms of their weight, the deviation between weight and their expected value is also going to be positive. So they're on this side of the line. That's positive. You multiply two positive numbers together, and you get a positive number. If now we go down here, here what happens if we take height minus the expected value of height, what we get is a negative number. And if we take weight minus the expected value of weight, it tends also to be a negative number. You multiply two negatives together, and you still get a positive number. So this is the concept of positive covariance. In this plot, what we've got is the size of the vehicle and its fuel efficiency. So again, we've got our guidelines drawn at the expected values. So if we think about these guys here, in terms of their vehicle size, it's less than expectation. It's going to be a negative number. When you think of their fuel efficiency, it's going to be greater than expected. It's going to give a positive. You multiply those two things together, you get a negative. Now let's think about these guys down here. These guys down here, in terms of their vehicle size, you take the vehicle size minus the expected value, you're going to get a positive. But we can take the fuel efficiency minus the expected value of fuel efficiency, you're going to tend to get a negative number. Multiply positive by negative, you get a negative. So this example is one of negative covariance. So these are all simulated data. I made these data up myself. So I know what the covariance was here. And the covariance here was 4.5. That's the value of the covariance. But the problem with covariance is that number 4.5 isn't terribly informative. So normally, instead of speaking of covariance, we tend to speak of correlation. So how do we calculate our correlation, which you typically represent as rho? We take the covariance, take this covariance value here, and we divide it by the product of the standard deviation of the two random variables. And when we do that, in this particular case here, what we get is a value of 0.9, which is really understandable because we think about correlation. We think of a value that goes from -1, very strong negative or perfect negative correlation, +1 perfect positive correlation with 0 in the middle. So we've got a very strong positive correlation here. So we've got this formula, and we can take this formula and we can just rearrange it. So I just rearrange this formula, and where we get is the covariance between height and weight is equal to the correlation coefficient rho multiplied by the standard deviation of height multiplied by the standard deviation of weight. And that's exactly what we have in these two corners. So that's just an overview of this concept of covariance and the covariance matrix.